All right, let's take a look at early models of the atom, Dalton to Rutherford. And in earlier science classes, you learned about the atom, and that's the smallest part of an element. And you learned about atomic structure. And if you take a look here, we have three different blanks for subatomic particles. Protons are the ones that have a positive 1 charge. They have a relative mass of 1 atomic mass unit, and they're located inside the atom. And then the neutrons are the other particles that have a relative mass of 1 atomic mass unit. They don't have a charge. They're also inside the nucleus. And then the particles that are outside the nucleus are electrons. They have a negative 1 charge, and they do not have, their mass is so close to 0 that we say that they don't have a mass. The two subatomic particles that are responsible for almost all of an atom's mass would be our protons and our neutrons. And most of an atom's volume is actually empty space. Let's take a look at the ancient Greeks. Okay, so about 25,000 years ago in ancient Greece, we had a philosopher and a student. The student was Democritus, and they reasoned that if a sample of matter could repeatedly be cut into smaller and smaller pieces, the result would be a particle so small that we couldn't cut it anymore. And Democritus termed this an atomos, which is Greek for uncuttable, and we use that to refer to the smallest particles of matter. Now, Aristotle proposed that matter was made up of earth, air, fire, and water. And those were the 4 basic elements of his time, and that was embraced for about 2,000 years in the practice of alchemy. And if we go to the next page here, we're going to talk about the last half of the 1600s, where the first real scientist emerged. His name was Robert Boyle. He was the first person to perform and publish some results from experiments, and in 1661, Boyle published something called The Skeptical Chemist. This outlined the scientific method. Further studies over the next 140 years by other scientists like Carl Scheele, Joseph Priestley, Antoine Lavoisier, and Joseph Proust resulted in mass laws governing compound composition, meaning what compounds are made of, and chemical reactions. And this was used by John Dalton to propose something known as the atomic theory. Now, the atomic theory says that all matter is made up of atoms, and it can't be broken into smaller pieces. It can't be created or destroyed. This is going to fall apart later when we talk about nuclear chemistry, created and destroyed. Number 2, the atoms of an element are all identical to each other. Not all atoms of the same element are identical, and you learned about this when you talked about isotopes in biology. However, atoms are different from other elements. Atoms of one element are different from other elements. Number 3, atoms of different elements combine in ratios to make compounds. And in a chemical reaction, atoms are separated, rearranged, and recombined to make new compounds. Let's take a look at this quick check here. Suggest a reason why. Robert Boyle is often called the first true scientist. Well, he's the one that introduced scientific method. And he's the one that insisted that experiments are required to gain knowledge about the world around us. Number 2, Democritus and Dalton both proposed the existence of atoms. How is the development of their ideas different? Well, Democritus was using intuition. Whereas Dalton based his conclusions on experimental data. Number 3, Which part of Dalton's atomic theory is now known to be incorrect? Well, number one, let's throw something out there that I haven't mentioned yet. Subatomic particles are technically smaller than atoms, right? Number two, isotopes are atoms of the same element with different numbers of neutrons. And then number three, when we look at radioactive decay, it may create or destroy atoms. Which is kind of cool. Okay, let's talk about discovering the subatomic. In 1859 and between 1859 and 1879, Julius Plucker and William Crookes in England were using some special glass tubes. And Crookes worked with a sealed glass tube that was connected to a vacuum pump. And you can see that in this figure here. The tube contained a negatively charged electrical terminal, which is known as the cathode. So here is your negative end. And they have a positive terminal known as the anode down here. About halfway along the length of the tube. And then there's a broad flat cross that was placed about 2/3 of the way down. And when you apply electricity across the electrodes as the air is being pumped out of the tube, any air that's remaining in the tube starts to glow. And we call that fluoresce. So it's fluorescence, fluorescencing, I guess you could say. The glow faded as the air was removed, but close inspection in the darkened lab revealed a shadow of a cross surrounded by a faint green glow at the end of the tube opposite the cathode and a very faint glow coming from the cathode itself. The location of the shadow and the cathode's glow led Crookes to conclude that something was traveling from the cathode to the other end of the tube, even though all of the air was gone. Now, in Paris, Jean-Baptiste Perrin discovered that if you put a magnet next to the tube, it deflected the mysterious beam. And because Perrin knew that only a beam of charged particles could deflect a magnetic field, he concluded that the cathode ray was a stream of charged particles. Now, Joseph John Thompson, also known as JJ, in 1897, he modified Crookes' tube by passing the cathode ray through a hole in the center of the anode, and that's what this image is here. And he directed it onto a fluorescent target. And he focused the cathode ray by deflecting it towards a positive plate. So here you can notice that the cathode ray is coming in. Here is my positive plate here. And it is going towards that positive plate. And you know that opposite charges attract. So that means that if I have a positive plate and the ray is attracted to the positive plate, the ray has to consist of negatively charged particles. And so he was able to calculate the magnitude of the charge to mass ratio for these particles. And he found that it was 2,000 times greater than the charge to mass ratio for hydrogen, which was the smallest particle that was known in 1897. So Thompson actually discovered a particle that was a lot smaller than the smallest atom known at the time. Now, on the next page, in 1897, J.J. Thompson gave a speech, and he told his audience that cathode rays were actually tiny negatively charged corpuscles of electricity. And in 1906, he was awarded the Nobel Prize. He actually discovered the electron. That's what these corpuscles were. And in 1897, he said, you know what, if there's something positive in the atom, there has to be something to counter its negative, counter that, and we balance it out with a negative charge. So he suggested that in 1903, the atom should be described as this spongy ball or plum pudding that had a dense positive charge with negative charged electrons dispersed evenly throughout it. He called this his plum pudding model. Let's take a look at the quick check at the bottom of the page. So the electron's charge was determined in 1909 by Robert Millikan to be 1.602 times 10 to the negative 19 C. Use the charge to mass ratio, that's what E over M means for the electron, to calculate the electron's mass in grams. Okay, so if we're going to use this value and this charge to mass ratio, you should be able to cancel the C unit, which is coulombs, to give me grams. So I'm going to go ahead and start with 1.602 times 10 to the negative 19 coulombs. Put the coulombs on the diagonal and grams on top. The 1.76 times 10 to the 8th goes with coulombs. The 1 goes with grams. This would be 1.62 second E negative 19 divided by 1.76 second E 8. You're going to get 9.10 times 10 to the negative 28 grams. Now, number 2. What evidence led Crookes to conclude that the unknown ray in the vacuum tube originated at the cathode? Well, there was a faint glow. Of the cathode, and there was a shadow of the cross at the other end. And letter B was a beam of charged particles. Well, it was deflected by a magnetic field, that cathode ray. C, may be a beam of negatively charged particles. So the beam traveled from the negative terminal, which was the cathode, to the positive terminal, which was the anode. And opposites attract, so the negative particles travel to the positive anode. We have one more question on the next page. Identify the two most important components of Thomson's atomic theory. Well, the atom isn't the smallest particle of matter. Subatomic particles are. And letter B, subatomic components of an atom are oppositely charged. Now, let's talk about Ernest Rutherford. In 1895, he won a scholarship to study at the University of Cambridge with J.J. Thompson. Afterwards, he went to McGill University in Montreal, and he was studying radioactive emissions. And Ernest Rutherford and Frederick Soddy actually discovered 3 types of radioactive emissions, and they were called alpha particles, beta particles, and gamma rays. And those are summarized in the table here. Alpha particles are a helium nuclei. Their symbol is this here. And they penetrate a few centimeters of air, but you could stop them with a thin sheet of aluminum foil. If we're talking about beta particles are high-speed electrons. They penetrate a few millimeters of aluminum, but I can stop them with a thin sheet of lead. That symbol looks like this. And then gamma rays are not particles. They are not matter. They're high-energy waves. They penetrate about 30 centimeters of lead or 2 kilometers of air. And this is the symbol for a gamma ray. And in 1909, Rutherford returned to England, and he was using alpha particles to test the makeup of the atom. And he was aiming alpha particles at a really thin sheet of gold foil. And he did an experiment known as the gold foil experiment. And he believed that nothing in Thompson's spongy atom was actually capable of altering the path of these alpha particles. So he was expecting them to pass through the gold foil without deviating from their path. But what was interesting was the majority of those alpha particles behaved as predicted, and they went right through the foil. But a few particles deviated through large angles, and very few didn't go through the foil at all. They bounced back. So this is an image of his gold foil experiment. And Rutherford explained those results by suggesting that the mass of the atom was in a really, really small place. It was a dense positive structure, and he called it the nucleus. And it was surrounded by a cloud of negatively charged electrons, which accounted for most of the atom's volume, but none of its mass. And Rutherford's model of the atom looked more like a planetary system with electrons orbiting the nucleus. He received a Nobel Prize in 1908. He thought that there was some sort of a neutral particle that also existed that added mass but had no charge. And 20 years later, James Chadwick discovered the neutron. Now, the summary of the 3 subatomic particles is given for you in this table. We tend to use the relative mass, not the absolute mass. And if we go to the next page, I want to point out one thing. They give you the abbreviations for protons, neutrons, and electrons within that table. Let's go to the next page and look at the quick check. Why did Rutherford believe that the nucleus was so small compared to the size of the atom itself? That's because a tiny fraction of alpha particles deflected. Number 2, why did Rutherford believe that the nucleus had a positive charge? Alpha particles are pretty massive, and the positive charge is what allowed it to be deflected. So alpha particles are massive and positively charged, so the nucleus must also be in order to deflect it. Number 3, to what parts of the gold foil experiment was Rutherford referring to when he used the following analogies? So a 15, I'm trying to find, here we go, a 15-inch shell. So that would be a fast-moving, massive alpha particle striking the atoms of gold foil. B, a piece of tissue paper. So Rutherford originally considered the atoms of gold foil to be to resemble, according to Thompson's plum pudding model of the atom. So number 4. Experiments show that the diameter of the nucleus of an atom is about 10 to the negative 14th, and the diameter of an atom itself is about 10 to the negative 10th. If the diameter of the nucleus was actually 2 centimeters, the width of your thumb, determine the diameter of the entire atom. Well, if you take 10 to the negative 10th divided by 10 to the negative 14th, you're going to get 10 to the 4th. So this is the relative size of an atom compared to the nucleus. So if the diameter of the nucleus is 2 centimeters, then the size of the atom is going to be 2 centimeters times 10 to the 4th, which is 2.0 times 10 to the 4th centimeters, or that would be the same thing as 2.0 times 10 to the 2nd meters. And this is about the length of 2 football fields. Okay, let's talk about atomic number. So this should all be review. The atomic number is abbreviated with the letter Z. It is the number of protons and the positive charge in the nucleus. The mass number is abbreviated with the letter A, and that equals the sum of the protons and the nucleus, and the neutrons in the nucleus. This is often shown with an atomic notation here, where you have the mass number in the upper left-hand corner and the atomic number in the lower left-hand corner. The atomic number can be excluded, and you simply refer to the periodic table to get it, or if they give you the number of protons, then you would fill it in. Now, if you're looking at a symbol, an element symbol with a dash and a number after it, that would be the mass number. So you will also see that atomic notation. Here, if I'm looking at 14N7, this 14 is the mass number, so you have a sum of protons and neutrons here. This is nitrogen. This is the atomic number 7. If I want to get the number of neutrons, since 14 is protons plus neutrons, and the number 7 is my protons, you would take 14 minus 7 to get 7 neutrons. This can also be written as N-14, which is nitrogen 14. Down here, I've got fluorine. 19 is the mass number, 9 is the atomic number. 19 minus 9 gives me 10 neutrons. This can also be written as F-19, which is read as fluorine 19. Now, one atomic mass unit, which is abbreviated AMU, is a 12th of the mass of a carbon-12 atom. And the atomic mass is the average mass of an element's atoms. Now, chemical changes never involve a change to the nucleus, but they will often involve a change in electrons, which can be added or removed, which create an ion. So for every electron that an atom gains, you will form a negative charge, which is an anion, as shown here in the upper right-hand corner. It is also acceptable to write it as P-3, which I tend to do, and I like to do that on Canvas. Now, if you are losing electrons, then you will form a positive charge, which is known as a cation, which would be here. Mg plus 2 would be your cation. That's the format that we tend to follow in this class and on Canvas. If we're taking a look at the practice problems here. Number 1, determine the number of protons, neutrons, and electrons present in each of the following. So if I have an atomic number of 20, I have 20 protons. 40 minus 20 would give me 20 neutrons. This plus 2 charge tells me I lost 2 electrons. In a neutral atom, the number of protons equals the number of electrons. So normally we would have 20 electrons, but 20 minus 2 would give me 18 electrons. For letter B, atomic number 52, 52 protons. 128 minus 52 is 76 neutrons. Negative 2 charge means I gained 2 electrons. Remember, if it's neutral, I have the same number of electrons as I have protons, but I need to add 2 because of that negative 2 charge, so I really have 54 electrons. In C, I've got 24 protons, because that's the atomic number. 52 minus 24 is going to give me 28 neutrons. I would expect to have 24 electrons if it was neutral, but the plus 3 charge means I lost 3 electrons. So that means I have 21 electrons. Number 2, write the atomic notation for these neutral atoms. Bromine 79, so that is my atomic number. And if I look, that is the mass number. And then if I look at the periodic table and I see 35, that is my atomic number. Gold 197, that's AU with a 197 in the upper left-hand corner. Its atomic number is 79. Thorium 232, that's its mass number, and then its atomic number is 90 from the periodic table. Now, if we're completing this table, you may want to pause the video, fill it in, and then check your answers. I'm just going to make a couple of notations. The atomic number is the same thing as the number of protons, so these 2 columns should match. To get the mass number, this is protons plus neutrons. So you're going to add these 2 columns together to give you the mass number. The electrons will equal the number of protons if it's neutral and there's no charge in the upper right-hand corner. Okay, so a couple of things to note. Here my protons are equal to the electrons, which is why there's no charge in the upper right-hand corner. Here I have 2 fewer protons than electrons. So I gained 2 electrons, which is why my charge is a -2. Mass number is in the upper left-hand corner. Atomic number is in the lower left-hand corner, which is the same as the number of protons. I have 1 fewer electron than protons, so I lost an electron, which is why I have a +1 charge. The +4 charge on thorium tells me that I lost 4 electrons, which is why I have 86 electrons. That's 4 fewer than the protons. Here, my protons and my electrons are the same, which is why there is no charge on the bismuth. Let's turn the page. Let's talk about isotopes and mass spectrometry. Okay. Isotopes are different forms of the same element with different numbers of neutrons. And the number of naturally occurring isotopes of an element and their relative masses and their abundance in nature can be determined by a mass spectrometer. So what happens is mass spectrometry uses the fact that charged particles moving through a magnetic field can be deflected from their path based upon their charge to mass ratio. So the greater the ratio, the more the deflection. So when you're looking at the image here, you will notice that your sample is entering and then it goes through a magnet and then it gets deflected here, and your least massive ions are going to be deflected the most, and your most massive ions will be deflected the least. So if we take a look at the sample problem down here, which gives us some data from a mass spec, you'll notice that we have 3 different isotopes for neon, the masses in atomic mass units that we've obtained, and their percent abundances in nature. I can use this data to actually calculate the atomic mass of neon. What you would do is take the mass of neon 20 times its percent abundance as a decimal. So use this as 0.9048. Then you add it to the mass of neon 21 times its percent as a decimal, which is 0.0027. Then you add it to the mass of neon 22 times its percent abundance, which is 0.0925. They've done that down here, and you will get 20.18 AMU for your result. And we tend to take our atomic masses to the hundredths place, which is 2 places past the decimal. We can also, if you take a look at the next page, we can calculate the percent abundances, since we know that the percent abundances add up to 100 for a sample. So let's take a look at some practice problems here, where in number 1, we are using the mass spec data to calculate the atomic mass of gallium. So the mass of gallium-69 is 68.9256 times the percent as a decimal, which is 0.6011. And then we're going to add that to the other isotope, which is gallium-71, which is 70.9247 times its percent as a decimal, which is 0.3989. And that's going to give you 69.72 atomic mass units. Notice I rounded that to the hundredths place. Okay. If you take a look at number 2, we want to figure out which isotope is deflected the most and which isotope is deflected the least. So the one that's going to have the most deflection is the one that's going to have, it's the least massive. So if I look at these mass numbers of 22, 21, and 20, because my charges are all +1. So this neon 20 will have the most deflection because it's the least massive, and neon 22 will have the least deflection, and then the other one will be in between. Okay, let's take a look at question number 3. Chlorine has 2 naturally occurring isotopes. Calculate the percent abundances of chlorine-35 and chlorine-37 using the following data. Okay, I have the overall atomic mass, and I have the mass of each isotope, but I have no idea what their percent abundances are. So what I'm going to do is I'm going to say that x plus y equals 1 and y equals 1 minus x. So I'm going to label this as my x percentage, my chlorine-35 percentage, and my y as my chlorine-37. So I'm going to take the mass of chlorine-35, and I'm going to multiply that by x, which is the percentage as a decimal. Add that to chlorine-37's mass times my Y percentage as a decimal, that equals 35.453 atomic mass units. Now, I'm going to substitute 1 minus X in here for Y so that I have one variable in my equation to solve for. You're going to distribute here. And then combine like terms, and you're going to end up with X is 75.76%. Okay, so chlorine 35 is 75.76% abundant. Now, if I take my Y is equal to 1 minus 0.7576, that's going to give me my 0.2424 multiplied by 100. Y is 24.24%. So that means that chlorine 37 is 24.24% abundance. And those percentages add up to 0. I'm sorry, to 100, excuse me.